so we are still within the methods to measure NMR spectra, or what we call hyperfine spectroscopy. And now what we did before was the ENDOR, and now we will do ELDOR-detected NMR and ESEEM spectroscopy. So these are different methods. So we've seen this before. So in ENDOR, it's an electron double resonance, or can be triple, but basically you combine microwave and RF. So you irradiate your electrons and you irradiate your nuclei. Now, when we look at ELDOR-detected NMR, it's a double resonance technique again, but it uses only microwave frequencies, maybe 1, maybe 2, maybe 3. So let's see how it works. So remember I talked about the hyperfine interaction, and we sort of took only the secular term, but now I put the full hyperfine matrix. And now we have the different states. So now we have, above the alpha, so the blue one is for the electron, the black is for the nucleus, and then we have different types of terms. So the terms that are on the diagonal terms, they will depend on TZZ and AE. So you remember that T is the T perpendicular, T parallel is basically just the proportional to 1 over the distance when it is the point dipole. So this comes on the diagonal. Then we have the red terms. Yeah, so the red terms, you see what they connect? They connect nuclear states within the same electron state, right? So they connect for the alpha of the beta of the nucleus within the same state, and these are the TZX and TZY components. So now they are written it's not in the principal axis system, it's just in any axis. So then we have these red ones, and now we also have the green ones, and the green ones, we refer to them as non-secular terms, and they connect both states that change the electron and the nucleus, and these are not so important. So the two methods that we will talk about in this lecture depends on having the red terms. So they really depend on non-zero pseudo-secular terms. So you can imagine that we are exploiting forbidden transitions in order to see some nuclear information. So let's write again. You remember we've seen this Hamiltonian. We have the A term and the B term, and here are the 4-level systems. And you see the green ones are the allowed EPR transitions. The blue one are the allowed NMR transitions, and then these red ones are forbidden EPR transitions, where you change the quantum of the electron spin and the nucleus spin. Now, if we want to write down the allowed EPR transitions, so they are given by here. It's the Ni is the center, the frequency, plus and minus A over 2. And I neglected this B term because let's suppose we work at high field. So it doesn't affect the frequencies, or a little bit. And the forbidden transitions are given by, you see, it's Ni14, Ni23. And it is the same as the allowed transitions, but it's shifted by plus and minus omega n. OK? So while the allowed EPR transitions don't have information about the nucleus, the forbidden already have. If I could measure them, I would know if I have a proton or have a C13, right? Because I have the Larmor frequency there. So how the spectrum looks like. So now these are the Ni24 and Ni13 are the allowed EPR transitions. Yeah, they are centered at the G, or if you do it by pulse, by delta Ni, and yeah, they are split by A. And then we saw that the forbidden transition are just shifted by the nuclear frequency. So you have here the difference between Ni24 and Ni14 is Ni alpha, and the difference between Ni13 and Ni14 is Ni beta. So now what is the probability of these forbidden transitions? So they are usually small. We saw many, many spectra. We didn't see many of them, right? So what is the probability? Yeah, so they're related to some angle. And we see that this angle is the arctangent of B over A plus 2 Ni n. So if B equals 0, we don't have forbidden transitions. Yeah? So this is for the alpha, and this is for the beta. And you see that the intensity goes like sine square eta. So the largest is the difference between the two, then the larger will be this transition. Okay, so what do we need to observe in forbidden transition? We need to have anisotropic hyperfine coupling, and the B term has to be significant. So in the cases that A is on the order of Ni n and B is bigger than 0, these become very significant. So you already know by heart how we do Davis ENDOR, right? This is pretty simple, right? Look at the side. This is the Davis ENDOR. We initially have a selective pulse on one transition. Yeah, we invert the population. Then with the RF pulse, we move it to the other manifold, and then there's no population difference, and here comes our signal. So, right, so what do? We do microwave RF, yeah? But, you know, you could do maybe a shortcut. So imagine that instead of going in 2 steps, you go in 1 step. So instead of going microwave allowed, RF allowed, you go straight on the forbidden transition. So this is here on the right. So this is ELDOR-detected NMR. So it's electron double resonance detected NMR. Often you see it as ED. So what do you do now? You observe this transition, yeah, with the echo. So you observe the same one. But instead of giving this whole big thing there with the invert, what you do, you just give a strong pulse on the forbidden transition. Why do you need to give much more power? Because it's forbidden, so the nutation frequency is much, much lower, and you need to give more power. So this is called high turning angle pulse. So if I do this, I arrive to the same situation. So if I will measure the difference between Ni0 and Ni1, yeah, it's the difference between the allowed and the forbidden transition. And you see, right, the difference in frequency between the allowed and the forbidden is the NMR frequency. So that's a very easy way to, provided that your signals, that your forbidden transitions are a little allowed. So actually, this experiment was suggested in '94, but it took for it a long time to be used because at X-band, it is not very useful, and you will see in a minute why. So only when high field became more established, we started to use it. So just to remind you, what are these nuclear frequencies? They are given here by this equation, and again, you have the B term. So for the frequencies, you don't really care about the B term, but when you calculate the energies, then the transition probabilities, it is important. So let's see an example. So what you usually do, you watch your echo at one frequency, you call Ni0, you sweep the second one, and you plot the difference. Okay? So now at 0, you will have the two of them overlapping. So this is just giving a huge long pulse on this transition, which basically saturates it. So at 0, you get a big hole. Right? So you see the hole in the middle, right? So now this spectrum has been inverted. So instead of being negative, it's positive, but this was just done by multiplying by -1, so it helps to see. So at 0, you see a very sharp line. So this is a copper histidine, and now if we go, you see the two nitrogens. Yeah, so this is the two signals, the two manifolds of the nitrogen. This was done in a deuterium solution, so you even see the signal of the deuterium, and you see some broad that is of the copper. So now what happened, so this is a W band, but then what happens if you work at X band, everything is very close to this hole, and then it's very hard to see. But when you go to higher field, it's really dispersed. And this, to record this took very fast, and if you have to do the ENDOR of these nitrogen, this would have taken much longer time. Yeah, so here is one example. And here is another very nice example. And so this is water, this is manganese 2 with 6 water molecules coordinated. And here they looked at the O17. They wanted to look at the O17. So now this was done such that, you see, this is the positive. You see the upper one is the left side. The low is the right side. And actually, it's enough to record only one. And then they remove the central hole by fitting it to a Lorentzian and subtracting it. And now you see very nicely. So you see basically they are the same, the two sides. And then you go and you see one doublet around 20. And this is a very nice doublet. This is of O17. And then you see the center is from O17 molecules that are far away. And then you see the next to it, there is a little dotted arrows that point to weaker pulses. And these are the double quantum lines of the O17. You can see that the first one shows up at around 18. So now the first one of the little peaks is around 36, and the other one is around 21, and it shows about 42. Okay, so we see very nicely the O17. To do this by ENDOR would have been very difficult. So for low gamma nuclei with quadrupole interaction, this forbidden transition becomes more allowed, so it's possible to see it. And these quadrupolar nuclei anyway have broad lines, so this technique usually gives broader lines. But if it's broader anyway, then you don't care. And what's nice here also, you see the proton. So the proton, this method is not very good for the proton. You've seen very nice powder pattern with ENDOR. When you do this method, you lose this resolution. So if you want to measure protons, I wouldn't do ELDOR-detected NMR, but N14, O17, this would be probably much easier than ENDOR. And then what we see here very nicely, we see the manganese line. So these are lines of manganese 55, which are very strong, and then you can derive from them the manganese ENDOR. And then there are some combination lines, I think, from the manganese and the oxygen, but these are the satellites. I don't want to dwell on them. So here is an example of using it of something that was just not manganese with water. So this was a polyoxametallate, is this big molecule that is a catalyst, and it has two. It has vanadium in it, and if it's reduced, then it has a spin. It's spin 5. You have a typical spectrum of vanadate. Vanadium has 8 lines because it has a spin of 7/2. So all these couplings, they come from the hyperfine to the vanadium. Remember, for manganese we had 6. For here we have 8. So then you sit on one of these lines, and you do your ELDOR-detected NMR. So so in the middle you see this big hole. Here it was not subtracted, and you see here the signal of the molybdenum. This, I think, the natural abundance is, I don't know, maybe 15%. And then you see of the O17, actually the central line overlaps, right? So you see one shoulder on the big central line that belongs to the molybdenum. Then there's another line that overlaps both molybdenum and O17. And this can be separated by a 2D method that we will learn about it later. Okay, so now let's see what happens with the nitroxide. Yeah, so you see this experiment can be very useful for nitroxide. So this is the nitroxide spectrum in W band. You remember it? Yeah, we saw it. We simulated it. So now we sit on this single crystallite position. Yeah, so we sit on the G parallel position of the Mi minus 1. So let's now look at this energy level. So because it's spin 1, yeah, it's 3 up and 3 down. We know that. If we look at the NMR transitions, for each manifold, we have 3 transitions, 2 single quantum 1 and 1 double quantum, and the same for the upper one. And then we have the allowed EPR transitions and the forbidden one. Okay, so now we sit here. So we are sitting on that particular EPR line. This is the green thick arrow. And now we scan, and we're looking for the forbidden transitions. So all these red dashed lines are forbidden transitions associated with this line. So they have one energy level in common with it. So if I take a difference between the allowed transition and any of these red dashed lines, I can see NMR transition, and these are noted in blue. So I will be able to see the dq beta. Yeah, this will come from the green, the thick green, and the dashed line, the line that is most on the right, right? The difference between them is dq beta. And then the same thing, you can identify all these differences, okay? So now if I now do my experiment, I should see 4 lines in this spectrum. And here we go. We have 4 lines. But there's one more, right? There is one more in the middle. And the one more in the middle comes because when we do this very strong pulse, there is some off-resonance effect, and we are hitting also this other allowed one. And this gives us also an effect. Okay? So this allowed one will give us, it will be at the difference, exactly the difference of the hyperfine coupling, because the difference between the 2 allowed EPR transition is the hyperfine coupling. So now if I can get these transitions, I can immediately get the hyperfine and the quadrupole and all the information that I need. Okay, so you can do this in 1D, but in principle, you can do it in 2D. Because sometimes you get these lines and there are too many and you want to resolve them and you want to correlate them. So then you can just do an experiment that has 2D. So this A is the single quantum experiment, and then you can do the sickle frequency, and then this is a double frequency. So here you sweep HT1, and then you add another, and you sweep the HT2. So then let's see what happens. So this is our spectrum, yeah, the one that we've seen before. Now the lines are upside down. And now you get these correlations. So you see blue lines are negative, and the blue lines correlate peaks that come from different manifolds. So you see it correlates the line around between 50 and 60 that belongs to the beta manifold with the line around 40 that belongs to the alpha manifold. So we have a line that is a bit weaker when we go along the diagonal, and again it correlates a line at the double quantum, yeah, with the single quantum from the other manifold. So this is what you get, and then you get all other lines that are on the diagonal and off diagonal that are positive, and these lines are actually coming from complication due to relaxation and cross relaxation. These can be accounted for by simulation. So anyway, this is the cross peaks that you see, yeah, between alpha and beta. So it's always the negative, the blue lines are always between lines in different manifolds. So if, for instance, I have an overlap of two different paramagnetic centers, I will see cross peaks only between lines that belong to a particular paramagnetic center. I cannot see from one paramagnetic center to the other. Okay, so this was ELDOR-detected. This was ELDOR-detected NMR, and it has been used mostly in the last few years, and it's really very nice. So, for instance, if you with nitroxides, if you want to nicely resolve these two peaks that come from, let's say, hydrogen bond and non-hydrogen bond, then you can resolve them very nice. You can resolve them here, and not only, you don't have to go to very, very high field EPR. Okay, so now we go to electron spin echo envelope modulation. So this is the third family. So we had the ENDOR, we had the ELDOR-detected NMR, and now we have this ESEEM. And so we looked a lot at the two pulses, and we looked a lot at decays, but often when you look at an echo decay, you will not see just a line, exponential or whatever form, but you see this is modulated. They always would have this modulation. And now if you, so now this modulation is related to the hyperfine, to the anisotropic hyperfine coupling. So if you would Fourier transform this modulation, eventually you get your NMR frequencies. So for what I had to do ENDOR and RF and double and all this, here I do very simple measurements. I don't need to adjust anything. So even if I don't understand a lot, it's hard to make mistakes because you just have to adjust your pulses, and you get this modulation, you Fourier transform, and you see this. So let's see how this works. So you remember that we have this forbidden transition. In principle, what we will have when you do this experiment, so you give your first pulse, and then you bring your magnetization to the XY plane. But remember, there was this term in the Hamiltonian that was SZIX. So this is really mixing the nuclear state, so it's almost like giving a pulse on the nucleus. So what happens is when you give the 180-degree pulse, then you get what you call branching transition. So you will not stay on the same frequencies, but you will branch to all these other frequencies of the forbidden transitions, and eventually you will refocus only the allowed transition, but some magnetization were lost to the forbidden transitions. And if you then look at the echo intensity as function of time, it will be modulated by the difference between the allowed and the forbidden transition, which is the nuclear frequencies. You can go through the whole mathematics. It's a little bit complicated, but you will see. So if you do this whole mathematics for spin S equal half and I equal half, your echo will be, for a two-pulse sequence, your echo will be modulated, and this is the equation. So let's look at it. So the echo is a function of tau. We have 1 minus, then we have k, and this k is the modulation depth. And if we look at this k, it's given by, you remember we had this sine square, remember we had this eta before that was related to the intensity of the forbidden transitions, and it's given by b. So this is this b term, ni I over ni alpha ni beta square. So you have to have a b there. Yeah, if we don't have the, so you can, now you know that when we go to high field and higher field, the contribution of this will be much smaller, and the forbidden transitions are much weaker, and this ESEEM does not work so well at high field, but we will see that sometimes for some cases it does. So it really depends on the relative hyperfine and the relative nuclear Zeeman. So if we have very weak couplings, Ni alpha is about equal to Ni beta, about equal to Ni I, and then the modulation depth is given by B over Ni I. Now in this case, what you see, you will just see modulation, that is the nuclear alarm of frequency. So immediately you can tell, oh, I have protons, I have deuterium, I have something like this. So here you can just plug this B in, and for isotropic K, for the case of weak coupling, the modulation depth actually gives you information on B. So by looking, so some people analyze the modulation depths and get the information on K, and from this you can learn about R. And this depends on R to the 6th. While the dipolar interaction always gave us R to the 3rd, this is R to the 6th. Yeah, so then on top of this, we have just the echo decay due to the phase memory time. So we have, so all this you have to multiply by the exponential decay. So now let's look at this equation. So you see, you have, it modulates with omega alpha, and it modulates with omega beta. But also I have term that is omega alpha plus omega beta, and I have a term omega alpha minus omega beta. So the difference gives me the hyperfine, and the sum gives me, to first order, gives me the Larmor frequency. So if now I Fourier transform, then I will get a doublet. Okay, sometimes I write Ni alpha, sometimes omega. This is just a 2 pi difference, okay? So you see a doublet split by A at the Larmor frequency, and then the 2 little peaks, one at the difference and one at the sum. Now, if you have strong coupling, then it goes like this. The center line is split by twice the Larmor frequency, and it's centered by A over 2. And then you have the small peaks are the sum and differences, and this time they give you A and 2 omega I. So you have this information. So then you say, okay, so Daniela, why you bother with ENDOR, or why you bother with ELDOR? Just do this, and everything is great. But you can notice 2 things. First, usually the phase memory time is very fast, so these modulation don't live for very long, so your resolution is very low. And then we have the dead time, so we lose half of it. We lose quite a bit of it. So then when you Fourier transform, you get pretty ugly Fourier transforms. So this is just an example. So here, this is an ESEEM trace that was calculated with easy spin. So then you have to usually remove the decay. You remove the decay, you get these oscillations. And then normally you apodize, just like you do in NMR. You zero fill, and you do Fourier transform. And because we have problems of dead time, again you have these phase issues, and you have to take magnitude spectrum, and you lose your resolution. So now, when do you see very strong effects? So there is something that so as I said, the modulation will be a function of the ratio between AI and Ni. So when you are in a case that, so if you remember, you have the 2 electron manifolds, and they split by the Zeeman, and then the hyperfine would add to one manifold and would subtract to the other. So if the hyperfine is on the order of the Zeeman, you can end up like having no field, because so for one manifold, the hyperfine cancels the Zeeman. For the other, it adds up. So then when this happens, you have complete mixing. Your forbidden transitions are really very much forbidden. And here you can see that, so this, what we see, all these blue lines are the Fourier transform of these omega, of the two-pulse ESEEM. And you see them, you see that this line that goes to the right broadens and decrease. And then the other one, when it gets close to 0, the intensity gets very, very high and very, very narrow. Okay, so this is a condition that is easy to measure. So here we have, below is the weak coupling regime, the strong coupling regime, and then the middle is the matching regime. So what people try to do is, if you have a too large, so now it depends. If you have a sample that has a particular hyperfine, you will go and look for the spectrometer at where the NEI will be close. So this is referred to as multi-frequency. So for different hyperfine coupling and Larmor frequency, you have different windows. So many cases you see at X band, some at Q, and some at W. So for instance, in W, you will never see protons, but strongly coupled nitrogens you will see. Because the strongly coupled nitrogen has, let's say, a coupling of 20, and the Larmor frequency is 10. So this is exactly this condition. Yeah, so nitrogens are also relatively easy to look at W band. Protons, you always have to go low. So let's just see some examples. So this type of experiments have been done for many years. And here we have what it is. It is a solvated electron in an organic, in the deuterated organic solvent. And you can see these modulations. And if you look, you will see that this is done at X band. So you can see, so you can see sharp modulations, right? And then you see broader ones. So the sharp ones are the protons, and the broader ones are the deuterium. Okay? So because we have protons and we have deuterium. Here is just another, so this is the FT ESEEM of a copper nitrilo trimethylene triphosphate adsorbed on aluminum. So you have copper, so copper has the unpaired electron, and then you have here phosphorus, and you have aluminum. So you expect to see protons, phosphorus, and aluminum. And what do we see? You see here the first peak comes from aluminum, the second one comes from phosphorus, then you have twice the aluminum, which corresponds to omega alpha plus omega beta. And here you have the Larmor frequency of twice the phosphorus, the proton, and twice the proton, because you see these combinations. Now, in order to see modulations, you have your B1 has to cover both omega alpha and omega beta. Okay, so now what happens if we have several nuclei? So I have 2 protons, 3 protons. So in this case, one uses the product rule. So you can get the equation for one proton, and then same equation for the other proton, and then you multiply them. So immediately you see that you will get some combination lines, because if you multiply 2 cosines, you will see. Now, if we take this modulation depth to be sort of small, so it's like 1 minus epsilon. So if you multiply 1 minus epsilon square, you will get only like, you'll get 1, 2 times epsilon, and then epsilon squared that you don't see. So they like add up. And here is an So for n equal 2, we get 1 minus 2 epsilon and plus epsilon squared. The last one will be pretty small. So now let's see what we get here. So this is, again, a copper in some single crystal. So here we have only protons. So you see, you manage to see a powder pattern of the protons. And here is twice. This is omega alpha plus omega beta. We have here the low part gives us the hyperfine coupling. And then we have a peak at 3 times the protons. And this comes because of this multiplicity. Now, we have to look at something here. Because the ESEEM effect depends on the B term. So the angular dependence of the B term is given by sine 2 theta. So the maximum effect will be at 45 degrees. So if you do a powder pattern of this, what you get from ESEEM, you don't get these very nice singularities. You remember in ENDOR we had these singularities. We can immediately identify what is the parallel and what is the perpendicular, and it's very nice. If you do ESEEM, you get something like this. So you lose this information. Yeah? Because it's the canonical direction. When theta is equal 0, sine 2 theta is also 0. And when theta is equal 90, it's also 0. So we lose, there's no effect there. There's no intensity, and the strongest is at 45. So you get these line shapes that you cannot really tell. So that's why sometimes you still rather look at the ENDOR and get nice line shapes. But from this, immediately I can say, oh, I have a coupling of about, I can read from the maxima of these two spectra. So this is something to remember. Also, ELDOR-detected NMR, the intensities will be like this because they depend on the B term. Okay, so as we said, the 2-pulse is very easy to do, but when you do the measurement, it decays fast, the lines are broad, there is dead time, so there is an alternative, and you can do the 3-pulse. And in this case, it's the stimulated echo. And now what you do, you instead of looking at so you have the stimulated echo, and then there's a time tau between the first and the second. Between the second and the third is time t. And then after some time tau, you get the echo. Now what you do, you measure the echo intensity as function of the time tau, t. So you keep your tau constant, and you measure it as a function of time t. Now, when you do that, then the relaxation between the 2 last pulses is dependent on T1 and not on Tm. So you can accumulate much longer, and you get much highly resolved spectra. So then usually you use the 3-pulse. You still have the dead time problem because you see it goes like tau plus t. So if you have a fixed tau, this introduces your phase. But then now you can think you can do a 2D experiment, change tau and change t. So now when you do the 3-pulse ESEEM, things are easier because you don't get the sum and different frequencies. So although these sum and different frequencies have information, if you have several nuclei, they give you complications. You do the 3-pulse. And for instance, here is just an example. This is a spin probe that is put in a bilayer in D2O, so it interacts weakly with the proton and deuterium. And this is the 3-pulse. And now you do background subtraction. You end up with something like this. You Fourier transform, and you see a signal at the proton, and you see a signal at about 2 megahertz that corresponds to the deuterium. Now, if you look well at the deuterium line, what do you see? You see a sharp line on some hump. This hump comes from strongly coupled deuteron, and these are these that give this hydrogen bond. So it's the same thing we've seen before in a different form. Right? So these are the hydrogen bonded water molecule on the nitroxide. And in principle, you can analyze the modulation depths. So if you would put this, you would use spin probes where you put the spin label more to the end of the alkyl chain or closer to the head. You will see that and you are working in D2O. Then the one that is closer to the head will have a large D2O peak because it sees the water and the hydrophilic part, and the one that is buried would show a little bit, and people can use it to see what happens in the membrane when, if you had, let's say, if you add cholesterol, then do you get more water going into the membrane or less, and etc. So you can really probe the amount of water near the spin label by this very simple, it's a very simple experiment, and it's really hard to get it wrong. Okay, so now when we do and we talked about it, so when we look at this stimulated echo, then you remember we had all these unwanted echoes. Yeah, so we want to see a stimulated one, but because the pulses are never 90, so you get all these other combinations, and you can get rid of them just by doing this phase cycle. So for the first sequence, you will give all pulses along the same direction. Then for the second one, and then you put your detection on -y. Then for the second one, you will change the phase of the first pulse, and you will detect with the plus. You will add the data, and then you will subtract, and then you add, and then you get rid of these pulses. Because if you don't do that, and you start and you measure your echo as a function of this time t, some of them will go one on top of the other, and you would see sometimes these huge glitches. So you have to do this phase cycling. And this is the equation that one gets for the 2-pulse, for the 3-pulse echo. So this time, you see, you don't have the sum and difference frequencies. However, if you look well, you see you have 1 minus k over 4, and then you have a term that is 1 minus cosine omega beta tau that multiplies the time dependence of the alpha frequency, and then you have a term that depends on omega alpha tau that multiplies the oscillating part with beta. What this means, this is just like we had in MIMS ENDOR. This is blind spots. So you can see that you can set up your tau such that you just will not see omega alpha. And you can set it such so for a particular, when you set a particular tau, you get a spectrum, and the relative intensities of this transition will be dependent on tau. So this means that usually you have to measure at several taus. So sometimes you have something automatic that measures 20 taus, add them together, Fourier transform, and then you know you did not lose any lines on the way. So as you see, if something is too easy, you pay with resolution. So it's never a free lunch. So what are the advantages of the 3-pulse? It has high resolution because T1 is longer than Tm. You don't have combination lines. And if you want, you can suppress lines. So for instance, if I'm working with deuterium and proton, all small coupling, I can set up my tau that I don't see the proton and see only the deuterium. The disadvantages is the suppression effect, need to run on many taus. And then sometimes if you have one nucleus that induces very strong modulation, it kills the other, and you need phase cycling. Now it's not a big deal, but years ago when all spectrometers were home built, to add the phase cycling was a big thing. Now it's standards. And again, we have the product rule if we have more than one, but so now you see the product rule is different. So if you look at the equation above, you can break it into two. You can break it into a omega alpha term and an omega beta term. Yeah, the first one you will take as omega alpha. This is the one that is modulated with omega alpha, and the second one with omega beta, and they are given here. And now the product one is going on each one separately. With the two pulse, you multiply the whole thing. Here, you multiply all the omega alpha by itself and all the omega beta by itself. I cannot explain this intuitively. You go through the complicated mathematics, and it comes out. So I cannot tell you what's the reason for that. So here is here's an example. So this is here's an iron, low spin iron. This is ferric cytoglobin, so it's one of the globins with iron porphyrin, and this is the 2 pulse, and you look at it and you don't really know what is a it's like some of the deers, right? So you don't know. Okay, you say, okay, you know, I have something around 20, I have something around 10. Then you come and you do the 3 pulse, and you see they are much narrower, they are better resolved, and then you guess that this peak around 20 is probably some of the sum lines. So here is what I wanted to show you. So for different hyperfine couplings, you can have different windows. So and you can tune it to to optimize the effect. So here what we have is spin half, and yeah, it's S equal half and I equal half. And for the upper one is N15, is optimized for N15. This is the B term, and then we look at A15 that has 1.5 megahertz, 4 megahertz, 12 megahertz, and 28 megahertz. So if I want to see the 1.5 megahertz, I have to work at, you see, at the frequencies that is between 0 and 10. That's the blue one. Yeah, because if I will go to higher frequencies, then the K will be very small. For 4 megahertz, I should work with the green one. So this is between about 15, about 10. So this X band will be very good. And now I have couplings of 12. So the 12 already, I need to go to a higher frequency. So this is around Q band. And then if I have 28 megahertz, I really have to be around 90. Yeah? So if you're very rich and you have all these spectrometers, you go from here to here. If not, you try to do something else. Now, but you see for the protons, because it has such a high omega I, you just go up to X band. Above X band, it's very hard to see proton. Deuterium, it's also possible to see it at W band. Okay, so let's see, what do we see if we measure on the same system 2-pulse ESEEM, 3-pulse ESEEM, and ENDOR? So when we measure ENDOR, we see this Ni alpha, Ni beta equal intensity. It was hard for us to measure, but once we measured, it's easiest for us to look at. Yeah, we can analyze it more easily. If we work with the 2-pulse, we have the 2 single. Yeah, we see these 2 lines, omega alpha and omega beta, and we have this sum and difference frequencies. And when we do the 3-pulse ESEEM, then we see these 2 lines, but one can be big, one can be small. And for these 2, we have problems with dead time, and the line shape is not as self-explanatory as it is. You don't see, usually to see the singularities is very helpful because you immediately know where you are. And here are some information of some reviews. So now we are looking at the HYSCORE experiment, which is a 2D version of the ESEEM experiments we talked before. And you see the abbreviation is Hyperfine sublevel correlation spectroscopy. So the pulse sequence is very similar to the 3-pulse ESEEM. However, if you see in the middle now, between the two last pi/2 pulses, there is a pi pulse that has been introduced. So what does this experiment give us? It gives us correlations between the nuclear frequencies in the alpha and the beta manifolds. So if you look here in the bottom, you see our 4 energy levels for the system, for the very simple system of spin of electron spin half and a nuclear spin half. And here we see the 2 nuclear frequencies, Ni3,4 and Ni1,2. So we know if we do an ENDOR spectrum and ESEEM spectrum, we will see these 2 frequencies. And when we will do a HYSCORE experiment, we will get a 2D map, because in the HYSCORE experiment, we record the echo intensity as a function of the time T1 and time T2. So if you look here on the left in the bottom, you see the 2D spectrum and you see the correlation. So you see that the position of the of these 2 cross peaks, in one axis it gives us Ni1,2, and in the other axis it gives us Ni3,4. And if we look at the projection, we really see the usual ENDOR or ESEEM spectrum. So now how this experiment works. So after the first 2 pulses, we induce nuclear coherences, and normally they will just evolve during the time T1 plus T2. But once we put in the center a pi pulse, this pi pulse will invert the 2 different, it will invert the EPR transition. So what was alpha before now becomes beta. So during T1, for instance, they will evolve with Ni1,2. After we gave the pi pulse on the EPR transition, they will evolve with Ni3,4. So this is the information that we get from this experiment. Now, if we have just 1 proton and spin half, it's not very interesting. However, when we have a complicated system, then we learn quite a bit from this. So now let's see some examples that are maybe a little more complicated. So you know that we are often looking at the powder patterns, at frozen solutions, and if you remember, the hyperfine coupling is given by the isotropic part, A-iso, and then it has an anisotropic part with the angular dependence of 3 cosine squared theta minus 1. And then there is this B term that complicates things a bit, but let's forget it for a minute. Let's suppose we work at a high field. So if we plot the ENDOR frequencies, the nuclear frequencies, as a function of the angle theta, we see here on the left how Ni alpha changes and how Ni beta changes. So now if we do a HYSCORE experiment, for every angle, for every small crystallite, we have to plot, we have a correlation between Ni alpha and Ni beta. So if we look at this region where we have the smallest splitting, then this at the 2D map, it will look like, you see on the left, on the red circle, you see it will correlate these 2 parts. So you can tell from this smallest difference that this belongs to this particular angle. So now if we go to the largest coupling, then we get this blue correlation. And of course, you have all of them in between. So for the weak coupling case, what we get is a line that will be perpendicular to the diagonal, and the width of this line gives us the anisotropy. Now we know that we have cases where we have a strong coupling, and in this case, the coupling is centered about half the hyperfine coupling, and the splitting is twice the Larmor frequency. So we see that now the lines are parallel all the time, but what changes is their center. So now if we plot in this 2D plot each of these points for every different theta, then we will get a different pattern in the HYSCORE spectrum, and here the ridges of the powder will be parallel to the diagonal and not perpendicular. So this, by the way that these ridges look, we immediately can tell if we are in the strong coupling or in the weak coupling. So here, for instance, in the bottom, the difference between these two parallel lines is always twice the Larmor frequency. And in the top, the center would always be the nuclear Larmor frequency. However, you remember there was this B term, and I told you if we are in a high field, we can forget it. However, most of the experiments are done at X band, and often this B term cannot be neglected. So what it really does to the HYSCORE spectrum is we don't really have these straight ridges, but they bend a bit. And you can see here on the left how they bend. So instead of getting straight lines, we get this curved line. And if you have good resolution, then if you measure this curvature, you really can get you can extract the anisotropic part, and if you see here, you see that from the total ridge you can get T and A iso, but from the curvature you can get T, and this is very important because sometimes it's not easy to separate the isotropic part from the anisotropic part, and here you get immediately a number that is related to B. It has T square in it, and from this T square you can immediately get the distance. Now there is a way, if you want, you can plot these HYSCORE spectra not as a function of the frequency, but as a function of the frequency square, and if you do that, you get these straight lines, and up here on the right you get the equations, and if you look at this equation, you can derive from this the isotropic and anisotropic parts. I must say that this is not really used very often. People just look at the spectra that we see on the left, and then they just try to find this curvature. So if we want to see some examples, so this is some HYSCORE spectra that were recorded from the oxygen evolving complex of photosystem 2. It's a complicated cluster of manganese that has a spin half in that particular S2 state, and here they wanted to see the difference in the structure of this cluster. If this cluster has manganese, 4 manganese and a calcium. So on the left, we see the spectrum where the calcium has been substituted with strontium, and when you look at the at the ENDOR frequencies, you see the all these ridges of the protons, and you can really differentiate here between 3 different protons. It's a weak coupling case, and they are marked here as H1, H2, and H3. Now, if you look at, when they looked at the complex with calcium, then the spectrum is different. You see here they could recognize 2 more protons. So you can really differentiate here 5 ridges, and then they continue to analyze this and to learn something about the structure of this complex. So this I will not go into it, but you see that it's rather clear to identify the different protons. So now let's go to nitrogen. Nitrogen is a very, very popular ligand in biological systems. So often you have your metal ion that is coupled to nitrogen ligand, like in histidine. So nitrogen, we all remember, has a spin 1. So we have an electron spin half. So we have the alpha and beta states, and then they are split by the N14 nucleus. So each of these levels is split by 3 to 3. And here are the nuclear states, -1, 0, and 1 for each level. So in orange, you see the single quantum transitions, the nuclear transitions, and in red, you see the double quantum transitions. Now, the splitting of these nuclear states, nuclear levels, will be dependent on, of course, the nuclear Zeeman of the N14, on the hyperfine coupling, and the nuclear quadrupolar interaction. So in a HYSCORE experiment, we should see, for instance, cross peaks between all the arrows in the bottom level with all those in the upper level. Now, there is often a case which is called the cancellation condition, where it happens that the hyperfine coupling is on the order of the nuclear Zeeman. So, for instance, in the case that the half of the hyperfine coupling is equal to the Larmor frequency, then what happens is that in one of these manifolds, the hyperfine cancels the Zeeman, and it's like we have a zero field. So let's look up here. So you have the energy level diagram. So you see in the bottom one, we see first the splitting for the nuclear Zeeman. So the three levels up and down for the alpha and the beta split the same. But then comes the hyperfine, and the sign is different for the two different levels, because one has ms equals minus half, and the other one has ms equal half. So what happens is for the upper level, you see all these, the splitting that was caused by the hyperfine coupling by the Zeeman is cancelled. So you see they all come together. And then there is further splitting by the nuclear quadrupole interaction. We see from here that in the upper manifold, actually the frequencies that we see are the so-called NQR frequencies. So from these frequencies, we can very easily determine the nuclear quadrupole interaction of the N14. So these frequencies are given by Ni0, Ni plus, Ni minus, and or here up there they're called omega 1, omega plus, omega minus, and omega 0. So in the bottom we have the equation that gives us omega that Ni0 is a function of the quadrupole coupling constant E square QQ over 4H and of its asymmetry parameter. And then the same thing you get for Ni minus has a dependence of this K and eta and Ni plus. So you can see that you can immediately determine eta and the quadrupole coupling constant. And then there is also a double quantum transition that you can see from the bottom manifold. This transition is usually relatively narrow, so it's easy to observe it. And now, once you determine K and eta from the nuclear quadrupole coupling, from the nuclear frequencies, then you can plug it into the equation that gives you the double quantum frequency of the bottom manifold, and then you can determine A. It turns out that when you work at X-band, for instance, the coupling to the remote nitrogen of histidine is just in this region. So this method is very, very popular to identify histidine ligands, particularly with copper. So now let's see what happens in the HYSCORE. But before we do that, here is an example of a single crystal. So this is a copper coordinated to histidine. Now histidine, so there is the imidazole, and the imidazole has two nitrogen, one that is directly coupled and one that is remote. So the remote one is further away, and this is indicated by this little red dot. So it turns out that the coupling to this particular nitrogen is within the cancellation condition. So here is, this is a single crystal experiment. It's an ESEEM experiment where the ESEEM measurements were done for different orientation of the crystals, and we can see here, all the line. So because the crystal had two different molecules per unit cell, we can see here that each frequency is doubled. So let's concentrate on the bottom. You see there is Ni minus, ni 0, and ni plus. And you see that these really, you see straight lines. They almost do not change with relative orientation to the field. And this is what we expected because they are so cold in zero field. So we can determine rather easily these nuclear quadrupole frequencies. And then you can see the double quantum frequency of the manifold that is not in cancellation, and it has some orientation dependent, but it's not very large, and this gives us, it's in a frequency around between 3 to 4 megahertz, and then we see the single quantum transitions frequencies of the manifold that is not in cancellation, and you see that they are all over the place. So now, in principle, for a single crystal, we have, and let's forget now that we have two molecules per unit cell. Then we have three frequencies in one manifold and 3 frequencies in the other, and each one give a cross peak with all. Each one give a cross peak with all the frequencies in the other manifold. So we should see 9 peaks, and because they are symmetric relative to the diagonal, we should see 18 cross peaks. And in this case, because we have 2 molecules per unit cell, we actually should see even more. So this is how a HYSCORE spectrum look like. And just let's concentrate here. So you see this is the double quantum, the cross peaks involving double quantum. So you see they are split. So these are the 2 different molecules in unit cell. And then you can go one by one and you can see all the cross peaks that they give. I will not dwell on that. That each one of you should do individually and quietly. But we all know that we usually don't have single crystals, and often we have frozen solutions or powders. So now we have, instead of getting dots for the cross peaks, we will get ridges, like just the first example that I showed you with the protons. So here, this is the case where we have HYSCORE of a frozen solution under cancellation conditions. So we know that we have 3 lines that are 3 frequencies that are field independent, and then we have other 3 that are orientation dependent. And in this case, we will have, this is a very narrow line because it involves the double quantum transitions of the 2 manifold, the one that has cancellation and the other one. So this should be the narrowest in this spectrum. Then we have this type of the green ones, and these involve frequencies that are NQR frequencies from one manifold and the double quantum frequency from the other. All the rest will give us very broad ridges that sometimes you can see, but sometimes they are just too broad. So in principle, when you have a spectrum, you will see these lines of the green and yellow lines. So let's see an example. So this is azurine. Azurine is a copper protein that it has a copper, and it's coordinated to 2 histidines. So we should see 2 different nitrogen, 2 different remote nitrogens. Sometimes they are resolved, sometimes they are not. And you see here by the arrows, you see all the peak that involve this double quantum transition, double quantum frequency with the NQR frequencies, because it is in cancellation. And you can even resolve the 2 different remote nitrogens, and here you have them assigned very nicely. So you see, if you look at the bottom one, you have a cross peak at around 3.5 and 4.5, together with around 1 megahertz. So the 1 megahertz line is one of the NQR frequencies, and the 3.5 and 4.5 megahertz are the two double quantum transitions of the different histidines, and now you can go and you can learn something about the coupling, the hyperfine coupling that is slightly different for each of them, and that's why they have slightly different double quantum frequencies. This here it's a particular mutant of azurine. Now, what happens if we are not in cancellation? Sometimes you don't have, you're interested in a metal that is not copper, and you don't have, or you work at a different field, and you're not in cancellation. And here is just a sketch of the shape of the cross peaks, and you see they're very broad, they're all over the place. There are only two very narrow ones, and these are these two double quantum transitions of the upper and lower manifold. So many times it's just these that you see. This was just calculated for the case of a hyperfine of 5 megahertz. This is the value of K is 0.6 megahertz and eta is 0.5. And to be in the cancellation condition at X band, so we have a Larmor frequency of 1, so A has to be 2. So here A is just a little too big, and then we start smearing the lines, and we don't have this nice cancellation condition. So now let's see an example of this case, and this is a cytochrome C oxidase. Has it's an enzyme, and we're not going into the details of the enzyme, but it has what you call a copper A site. So here you have two coppers, and they are coupled. So you see they are very close to each other. There are sulfur bridges between them, and they have a total spin of a half. And you see that there is also a histidine coordinated to each copper. And then we can see again the remote nitrogen. So now if you look at the X-band spectrum, so now we don't see these nice lines where you see double quantum and the double quantum cross peak with the single quantum ones, but we see just double and double. So for instance here, these are the cross peaks, the red one, that come from this particular nitrogen. Now we know that when there was a single copper, then this was in cancellation, but now we have two coppers, and the spin is delocalized over the two of them. So then we expect to have half of the hyperfine coupling on each of these nitrogens, and then it will be half, it will be too small to be in the cancellation condition. So we see here just the double line, but then we see another one, and this is given by the blue. So here, this tells us there is another nitrogen that is coupled, and this is probably a nitrogen that is from a main, maybe one of the backbone nitrogen, and now this gives you information about this particular site. Okay, so here you could really identify a new coupled nitrogen that was not expected previously. So I said it's when you work with the under the cancellation condition, it is really very very convenient because you get the NQR frequencies. So now you can say, okay, what do I care about these NQR frequencies? What do I care about the nuclear quadrupole interaction? What do I learn from this? And it turns out that it is very, very sensitive to the electronic structure of this particular nitrogen. So and here there is a table that shows you the range of the quadrupole coupling constant and of the asymmetry parameter for different types of nitrogen. So if you have, these are all different type of nitrogens that you can find in biological systems, and they have different quadrupoles. So sometimes if you can measure the quadrupole, then you can go to this table and see where it sits. because there's some correlation between the type of different types of nitrogen would have different correlation between the asymmetry parameter and the quadrupole coupling constant, and then you can see which type you have. So these are particularly useful to identify nitrogen type of ligands. Okay, but you know, life does not start and end with nitrogen. There are also other nuclei that are of interest, and also, you know, not everything is a biological system. And here is a very nice example of phosphorus 31 HYSCORE on aluminophosphate zeolite, Alpo5, and in this particular one, it was doped with titanium, and titanium 3 sites were generated. So we have titanium 3 plus, it has a spin of half, and then you can see that it just from the structure, it should have quite a bit of phosphorus and aluminum around it. And it probably has some catalytic activity, and that's why this material was interesting. So what they wanted to find out is, first, is this titanium really incorporated into the framework of this material, or it just sits absorbed on the surface, and what is the different and what is, so to do that and to determine this, they have to determine the environment. So the one thing they did, they measured the HYSCORE spectrum, and this was measured here in X-band, and you can see the ridges and the assignment. So you can see, for instance, if we look at the upper spectrum, and let's look, for instance, at P2. So you see two ridges, and their center is at the Larmor frequency of phosphorus, so that's how you know that this is a phosphorus signal. And then there is also some ridge, but it's like a little square that shows up on the diagonal at around close to 4, and this is an aluminum signal. So the fact that we see strong coupling for phosphorus and weak coupling for aluminum, we know that the titanium is situated in an aluminum site, so it has many phosphorus ligands around it, and the aluminum are further away. And in the HYSCORE, if you remember, we said that the peaks that are perpendicular to the diagonal have weak coupling, and these are P2 and P1. And then if we go on the left quadrant, we see that we have ridges that run parallel to the diagonal, and we can see that it's P3 and P4. So from here, it's really easy to find 4 different types of phosphorus with 4 different hyperfines, and this can be analyzed. Then they looked at it with, so the top one had no water, it was dehydrated, and then they added the water. So you see in the bottom spectrum, you see again all these different types of phosphorus. We have 4 types. We see the aluminum, but now we also see a very large ridge of proton, and this tells us, and we see that it's very broad. We can measure this coupling, and it gives a coupling of a splitting. You see that is almost 10 megahertz, and this tells us that this is probably water ligand. So when it is hydrated, we see water ligand. So really, these spectra are very, very nice and very, very informative. One other last example. So here let's see the effect of the magnetic field. So here is a polyoxometallate. It is reduced. So you see it has a vanadium 4, and this vanadium 4 has a spin of half. So you run a HYSCORE experiment, and this particular sample was prepared in 2017 because there was some interest in identifying where this vanadium, paramagnetic vanadium sits. And here is the HYSCORE spectrum that was recorded at X-band. So we see here on the left splittings from ridges belonging to weakly coupled oxygen, but on the left we see two sets of cross peaks, one belonging to the molybdenum and one belonging to the O17. And they overlap. And then, of course, there's the protons far away, so we know that there are large proton couplings. But the interest was in the O17. So how can we really separate them and see that it's really oxygen and molybdenum and not maybe two types of molybdenum or oxygen? So you can do these experiments also at W band, which is 10 times higher than X band. And now you see that they are nicely separated. So in X band, they are in the strong coupling regime. But when we go to W band, they become in the weak coupling regime. And you see here the oxygen lines, the center is in 20 megahertz. This is the Larmor frequency. And in the case of molybdenum, the center of these two cross peaks is 10. So at high field, there is a difference of 10 megahertz in their Larmor frequency. And at X band, the difference is much smaller. So they appear at 2 and 1 megahertz. So if you look at the difference between the cross peak, you can really identify it. So in principle, you can do high scores also at high fields, and it also depends always what is the size of the hyperfine. If it's small, if you go to if it's small relative to the Larmor frequency, then it will be very difficult to see. For instance, to see the protons in HYSCORE at W band is very difficult, and you will not try it. You will just look at the X band or do ENDOR. So I think that with this I'm done. So I hope you are not too confused with all the different methods that we talked about, ESEEM, ENDOR, ELDOR-detected NMR, whether you do it at X band, Q band, W band. So I think this is the fun. So you don't always do the same experiment, and you have to think what is the best for each system. So, you know, at the beginning it's confusion, but then it's fun. And I think with this I've finished with this series.